don't need every single cranial because we've done them already, but now we've just brought back the trigeminal. We've brought back now 7 and 9 with our taste there as well. And even the hypoglossal we brought back too, because that one controls the tongue movement. All right. And so those are, though I can't ask every one of them. I won't because I have other stuff to ask, but I'll ask one or two for sure. Okay, absolutely. Right. And even for a lob ball, the strongest muscle of mastication would be the what? Masseter, right? Masseter. So don't forget the things you already learned in another class, because it all goes together. Right? Any questions? Any other questions on the digestive system? This is a pretty involved lecture test, as you probably realize. Yes.
The Brunner's gland?
Yes.
It's in the
Submucosa.
Mucosa.
Of the duodenum.
So does that releases bicarbonate ions too?
Yes, it does.
Okay.
And
So it's secretin and Brunner's glands.
yes, both are trying to change the pH of the chyme. Yeah, Brunner's glands are only in the duodenum. Okay. If you didn't like that name, you could call them duodenal glands if you wanted. Okay, you can do that too. There, doesn't matter. But they're again releasing bicarbonate ion, trying to change the pH of the chyme. Right. And where's chyme formed? In the stomach. Yes, chyme is formed in the stomach. All right. Chyme is formed in the stomach. And that is my last slide, right? I believe it is. So a little bit of a review, at least from renal. I won't do a whole lot of digestive necessarily, but this is included on the same one. Okay. This is a good review. I'm not completely satisfied with it yet in its entire content, but this is what I've used in the past, and as I teach the course over and over again, I seem to be, want to improve it. At least in my eyes, I seem to improve it, and more and more. So this review was good for, I think, last year or the year before, or something like that. But I'm going to add a little bit more to it as we go on. I like to make the course more and more challenging. So I think I've done it so far with this. So, but this is a really good review. I will post this review with a few additional items added to it. You won't know what the additional items are necessarily unless you take a picture of it and then compare. But these are some information, some additional points here. So when you study this, parts of the nephron, okay, those are easily identified on maybe a picture, couldn't they be? Like maybe this is the renal corpuscle, this is the glomerulus, this is maybe the PCT, this is the loop of Henle, the descending limb, the hairpin turn, this is the ascending limb, okay, or you've got the DCT, or you've got with the collecting duct, which is not part of the nephron. So these are parts I could draw on or put a line to. Peritubular capillaries, vasa recta, all parts of at least of a picture of a nephron that we can appreciate. So histological standpoint, what about some properties there, especially when you look at the glomerulus? What's the big deal about that? It's glomerular filtration. There's lots of answers to that kind of question there. But, be able to recognize that it is the visceral layer of Bowman's capsule, right? That's another name for that. And so when you looked at that, you have the endothelial cells or the one layer of flat cells, basement membrane, and then you also have associated with that filtration membrane those cells with feet, right? Called podocytes, yeah, podocytes, all right? That makes for a nice question too, podocytes, okay? And with the podocytes, they had the feet, and between the feet, they had filtration slits or slit diaphragm, whichever name you want to recognize, it doesn't matter. And then, with that filtration slit diaphragm was composed of what? Anybody remember? Two structures, really. Nephrin and podocin. Nephrin and podocin were structures that compose our filtration slit diaphragm. So what's the big deal about them? Besides remembering them, what's the big deal as far as their function in this filtration membrane? They're able to filter by... Well, yes, you're correct. She says size and charge. In that particular instance, I was looking for charge because they are negatively charged, but I know what you're saying. You're correct. That was my next question. How does this membrane filter? By size and charge. Size is because if we have these filtration slits and the slit diaphragms, and also we have our tiny fenestra in the endothelial cells, or this type of capillary that we have. So size and charge, right? Don't forget that one. And the reason is, I shouldn't share that reason. But the reason is, we don't want to forget that. That's something that is very basic and you should absolutely know. Size and charge. Don't mess that one up. Okay? All right, so the path of fluid, we know, oh wait, I should not leave that alone. What drives that filtration?
Pressure.
Yes, which we can call what? She's correct. Blood pressure, glomerular hydrostatic pressure, whatever you want, those are all acceptable. So that's the driving force. How do we evaluate or kind of modify this rate of filtration formation? What are ways that we can change the GFR is my question there. Macula densa cells, yes, and now we're talking JGA apparatus, or just JG apparatus, right? Macula densa cells, and they are sensitive to what? This is not going down my list, but what can you do? They're sensitive to macula densa are in the wall of the DCT, aren't they? Sitting right there, fluid flows past them. Saltiness and rate of delivery. Yes, so if the rate of delivery is too slow, what will they release acting on the afferent arterioles? Too slow now. Yes, nitric oxide, a potent vasodilator. Okay, what if the rate is too fast?
ADP?
ADP, potent vasoconstrictor. Okay, very good. Now we have another way, besides our, which is there, is the macula densa. Another way though is the myogenic mechanism. What's that involve? This is an intrinsic tube, isn't it? That involves what? The property of smooth muscle. Really doesn't matter where we're at. Smooth muscle has that property. As soon as it stretches, immediate response is to contract. But since we're in the kidney, might as well call it that myogenic mechanism associated with the afferent arteriole, a way to regulate the pressure as it enters the kidney, okay, the blood pressure. What about an extrinsic way to modify the GFR? We're in the tubuloglomerular feedback, which we just did here, and then myogenic mechanism, or intrinsic. What about extrinsic? Things like NE from sympathetic nervous system, right? Sympathetic nervous system, right? And in that same discussion, we had things known as renin-angiotensin-aldosterone system. Okay? When will that system be activated? Then we'll get to the individual things that the letters stand for. When blood volume or blood pressure goes down. Okay? That renin-angio, and what does renin do for us? We know where it comes from. Cells of the JGA. Remember that. Okay? What does it do for us? Yeah. Yes, cleaves angiotensinogen into angiotensin 1, all right? Angiotensin 1 travels around in the blood, gets to the pulmonary capillaries, where these cells are very well endowed with an enzyme, ACE, especially pulmonary capillaries, all right? That's where that occurs, hence that's why I had that picture up there when we were trying to look at the whole pathway there, right? The lungs were up there. So we have angiotensin 2, okay? ACE is cleaving angiotensin 1 into the very active angiotensin 2, which is a potent what? Vasodilator, okay, or vasoconstrictor. Sorry, vasoconstrictor. So it's starting to become a vasoconstrictor. What are some ways that it wants to increase blood pressure? One, of course, is going like this, right? What another way that it might try to increase blood pressure or even the volume?
Stimulate higher blood.
Stimulate our what?
Blood.
Thirst center. Since thirst center cause release of ADH, right? ADH, what were you going to say? Yeah, also cause release of aldosterone, very good. And what does aldosterone do since you said that?
Makes the kidneys reabsorb sodium.
Yes, and it acts on what cells of the kidney? Nephron would be better, wouldn't it? Aldosterone acts on the, it is a principal cells located where? DCT and collecting duct, right? Okay. And what she had said is correct. It reabsorbs sodium. Water follows for osmosis, trying to raise blood volume, trying to raise blood pressure. Okay. All right. So we have our renin and now ACE enzymes discussed, and we have a little bit of angiotensin discussed as well. What we just included there is aldosterone, and might as well throw in ADH because ADH is going to be coming from where? Pituitary, that's perfectly okay, pituitary, and aldosterone is from the adrenal gland, that's perfectly okay too. ADH is going down to the same cells, principal cells of DCT collecting duct, telling them to do what? Well, yes, reabsorb water, yes, which raises blood volume and raises blood pressure. Okay. ADH also has another name. Did I give you another name ever? Because it is a mild, but it has effective vasoconstrictor properties. So sometimes it has an additional name called vasopressin. Sometimes it's called vasopressin. If you ever see that, that's extra. But if you ever see that, it's called vasopressin. It has some vasoconstrictor properties to it. Not overly effective, but it does have those properties. So if you ever see vasopressin, it's another name for ADH. Sometimes things come out of here. Additional words, but nonetheless. All right. So let's see. What's the diabetes mellitus? Right. Very good. Okay. When I mentioned that, I was interested, especially not in the whole, pathophysiology of diabetes mellitus, but the fact that uncontrolled, you can see glucose spilling over into the urine, right? And so, why does that occur? What's really the worry here? What has been reached? Yeah.
Capacity.
That's correct. Transport maximum has been reached. That's why we have glucose spilling into the urine. Transport maximum has been reached. Doesn't matter what the value is. You can look that up in some type of textbook, but with blood sugar values, it doesn't matter. But transport maximum has been reached. That's why glucose has been spilled over into the urine and is not reabsorbed. Most reabsorption takes place in the what? PCT, doesn't it? Most reabsorption takes place in the PCT because the presence of extensive microvilli, which actually I can show on a model in lab tomorrow. Be sure to look at that. You can see the microvilli on the model in lab. And even you can see the PCT, you can see the DCT, you can see the macula densa. You can even, to some degree, I don't like this presentation, but you can see the afferent and efferent arterioles. They're not as clearly demarcated as I'd like, but they're there too. So all these, even though they're microscopic, we have a microscopic model, so that's still fair game because anatomy just isn't gross anatomy, it's microscopic anatomy too. So we have to look at those. But you'll have those. You have a list of all the stuff you want to see. All right. So hyperosmotic, hypoosmotic, isoosmotic. What is that in reference to? Blood, which is an osmolarity of approximately 300 milliosmoles. Okay, very good. We already kind of know that. The countercurrent multiplier. When you think of that, what comes to mind immediately? What the loop of Henle, right? Immediately multiplier. When you hear things or see things like countercurrent exchanger, what comes to mind? Vasa recta. Very good. Okay, absolutely right. Now, if you look at the properties of the descending loop of Henle, what do you notice? On the descending limb, what happens?
Higher concentration.
Yeah, I'll buy that, but what happens as far as permeability properties go? Which is reflective of your osmolarity. Water leaves, right? And now in the tube, you have the osmolarity of the fluid going up, right? Becomes more salty, if you want, or saltier, if you want to say that. As it continues around the hairpin loop, what happens on the ascending limb? Now solutes are pumped out, water cannot leave, so now it becomes much more dilute, doesn't it? Okay, dilute. As it continues up, okay, up into the DCT, now we want to say, hey, we've got this 100 milliosmol solution or fluid here, but we don't want to keep this necessarily. All depends on the body's needs, but necessarily we don't. Let's say we don't. Now we want to be able to modify the osmolarity. How do we do that, though? There are permeability properties here that we can count on. So hormones. That's the big difference I want to stress is you want to change the osmolarity of the fluid in the DCT and the collecting duct. It's hormonally regulated. You don't see hormones acting on the PCT. You don't see them acting on the loop of Henle. You see them acting on the DCT and the collecting duct. That's how you can change the osmolarity. Hormonally regulated. That's a big difference, okay, as far as changing the osmolarity of these. All right.
What hormones are involved in that?
What hormones are involved in that? Yes, we have aldosterone, we have ADH, and there was another one included. No? A and P, which is what? Which is okay, I love abbreviations, I really do. Natriuretic peptide, ANP, okay? These are the hormones that act on it. I spent a great deal of time on aldosterone and ADH, and a little bit of time on A and P, but still included that one as well, because we want to be able to change the osmolarity, and we do change it in the DCT collected out with hormones. Okay? All right, let's see. Oh, they're all listed down there. Micturition, a fancy word for urination, right? Yeah. Renal calculi, which we'll talk about tomorrow in lab, or gallstones. Detrusor muscle is the what? Detrusor? Uh-oh. Yeah, you know they just, huh? This is the smooth muscle of the urinary bladder. That's what the detrusor is. Okay. What's the epithelium of the bladder? And other places too. Is it up there? It's not. It is transitional. Transitional, that's the epithelium. Alright, what about these last words, then we'll be done. Hematuria, what's that word for? Blood in the urine, should that be a normal finding? It should not be unless they get punched in the kidney. Proteinuria? Protein in the urine, is that a normal finding?
No.
It's not. Generally, you might get away with trace amounts, but generally not. Okay? Generally not. Okay? We have more words that we'll come across in lab, but they won't make their way onto the lecture test.
What's the glomerulus driving force, real quick? Understand the starting force is that the glomerulus driving force, what?
Yes, so what is the driving force here? At the glomerulus, driving force. What's the driving force for filtration?
Blood pressure?
Yep, blood pressure. Yeah, very good. Okay, that'll do it. I will modify this a little bit before I post it, but this is a pretty good review. I'm not totally satisfied.